Now that we have seen how stacks can be implemented, let's consider why this data structure is useful. It is important to understand in what kinds of applications stacks should be used. Stacks are ideal for any application that involves nested structures, and there are many such applications. Expressions are an example of a nested structure, so stacks can be used for a variety of applications that involve expressions. Evaluation of postfix expressions is one such example that we will discuss, but there are many others. Converting the format of an expression, such as from infix to pre or postfix, is another. All compilers use stacks in a variety of different ways. The parser, which is one phase of every compiler, typically uses a stack because the language syntax involves nesting. If statements can be nested inside of if statements, and so on. At runtime, compilers use a stack to store local variables. Once we have discussed recursion, it will be clear why the runtime system of any language that permits recursion must have a runtime stack. The evaluation of postfix expressions is the example we have chosen to illustrate the use of a stack. In a postfix expression, the operator follows its two operands. In most programming languages, expressions are written in infix notation, where the operator is in between the two operands. Postfix has the advantage that it does not require parentheses or precedence. Prefix notation has the same advantage. Many early calculators allowed formulas to be entered in postfix notation for that reason, and also because postfix evaluation is very straightforward. So before we look at the Java code, let's consider the basic pseudocode for the algorithm that evaluates postfix expressions. It involves repeatedly tokenizing the input and then performing an action based on whether the next token is an operand or operator. First, we consider what is required when it is an operand, which in our case will be an integer literal. What we do is push it onto the stack. If it is an operator, there are several necessary steps. We must pop two values off the stack, then perform the operation on those two values, and then push the result back onto the stack. When we reach the end of the expression, the stack should contain a single value, which is the final value of the expression. Here is the UML diagram of our example that evaluates postfix expressions that makes use of a stack. Having already discussed both the array stack and link stack classes, we know that they implement the stack interface. Both implementations potentially throw the two exceptions defined by the classes at the top. The class postfix-GUI contains the code for the interface to this program. We have separated it from the logic for performing the evaluation. Such separation is always a good design practice. Doing so would enable us to modify the program to use a command line interface instead by replacing this class without modifying the rest of the program. Because you should already be familiar with creating GUIs, we will forego discussing this portion of the program. But instead, let's focus on the postfix evaluator class, which contains the algorithm we just discussed that makes use of a stack. Initially, let's look at the whole class, omitting the details inside its methods. Like every class on the UML diagram, this class is inside the package stack. Using packages is our way of grouping the classes in each of our examples. There is one external package that we are importing, which is java.util. The class in this package that we need is the string tokenizer class. Although we only need one class in this package, we have used a wildcard rather than specifying the class. Some prefer avoiding this practice. We made this class public to allow it to be used by classes in other packages. The only instance variable of this class is the variable stack that will be used in the evaluation. Programming to an interface rather than an implementation is an important design principle. This declaration adheres to that principle because the reference type of this object is the interface type stack interface. The object type must be a class, of course, and in this case we are using link stack, but we could easily replace it with array stack without altering its behavior. This class will have two methods. The method evaluateExpression is a public method. It is the one that will be called from outside the class. In our case, it is called from the postfix GUI class. It is given a string containing the expression and returns its value. The method evaluateOperator is declared private since it is intended only to be called by the public method. It is provided the operator that is to be evaluated. Let's look at the bodies of these two methods, beginning with the public one, evaluateExpression. There are numerous techniques for tokenizing a string. Using the string tokenizer class has one important benefit, which is why we chose it. We prefer to require spaces between the tokens of our expression only when necessary, which is between adjacent operands. Because this class allows us to specify what delimits tokens and allows those delimiters to be returned as tokens, we can adhere to that requirement. Notice that we have included the four operators and the space as delimiters. Supplying the second parameter as true indicates that we want them returned as tokens. The first parameter is, of course, the string containing the expression to be tokenized. The algorithm described previously involves repeatedly processing tokens, which this loop will accomplish. We get the next token. If the first character is a digit, we assume it's an operand, so we convert it to an int and push it onto the stack. Note here that we are relying on Java's auto boxing feature to convert that primitive int to an integer object. Because we will also get spaces back as tokens, we must check that this token is not a space. If it isn't, it must be an operator, so we pass the first character of the token to the evaluateOperator method. Once there are no more tokens, the stack will have one value, which is the value of the expression, so we pop it off the stack and return it. Next, let's see how the private method evaluateOperator is written. The algorithm we outlined previously said that when the token was an operator, we first needed to pop two values from the stack, which is what is being done on this line. Notice that right is popped before left. The order must be reversed because a stack is a last in first out data structure. For the operators that are not commutative, like subtraction and division, the order matters. Next, we perform the evaluation using a switch. Unless you have been using the most current versions of Java, the syntax here may be unfamiliar. Not only are we using the syntax that uses an arrow rather than a colon, we are also using a switch expression rather than a switch statement. That syntax alleviates the need for break statements and the need for multiple assignments. Also, we are relying on Java's implicit autoboxing and unboxing to avoid explicit conversions between primitives and objects. Once the evaluation is performed, the result is returned. Okay, so let's take a look at this program now. And the first thing that I want to point out here is that we could take and modify this to be linked stack rather than array stack, and the program still compiles. So doesn't matter which one we choose. So let's leave it at link stack. All right, and then let's run this program. And for input, I'm going to choose an expression that has two operators, and we'll do multiplication and subtraction. And note also that I didn't put spaces between the operators. That was one of the requirements, that we had to be able to accept expressions that didn't have spaces anywhere except where they were needed. Okay, so when I evaluate that, I'll get a 4, which you can confirm is a correct result. And let me try one other thing here, just to point out that one thing we didn't do was we didn't check for correct syntax. So if we input something that's not a correct postfix expression, this is an infix one, we're going to see that an exception will be thrown. And of course we could make modifications to account for that as well. Okay, so although we used our implementation of the stack in this previous example, the stack class in the Java collection framework could have been used as well. So let's take a look at it. It has all the methods we defined and some others as well. Those include the most fundamental operations, push and pop. One operation that we did not include is peek, which returns the top element without removing it. Also included is a method to check whether the stack is empty called empty rather than isEmpty, which was the name we chose. Unlike our approach, there is only one implementation. It is implemented as a subclass of the vector class. This was actually a poor design choice, because it is not true that a stack is a vector. The proper relationship is that a stack can be represented by a vector. Both the vector and stack were included in an early version of Java before the addition of the complete Java collection framework. Had they been added later, most likely a different approach would have been used. The proper approach would be to use composition, not inheritance. That is, to create an instance variable inside the class of type vector, or perhaps ArrayList, which was a later addition. The reason using inheritance was not the proper choice is that the stack class inherits all the methods of vector. So it is possible to invoke the add method on a stack object to insert an element in the middle of a stack, which violates the last in first out property that stack should adhere to. In some languages like C++, language support is provided for representation inheritance. In such a language, making a stack a subclass of vector would not be a problem.